All right. So we have a huge crowd today, which is pretty awesome. I know we only have 5 viewers, but we actually secretly have roughly somewhere around like 15 questions to go through. So there's a lot of updates. Real quick, let me make sure all these adjustments are correct before we can get started. Perfect. All right, so let's talk about a few things. First off, we are back on YouTube Live. You guys missed us on Sunday. I actually had to post a video, and the video was regarding doing math tutoring, not live, but every Thursday and Sunday. I would post a video in response to comments that were from the previous tutoring session. We're no longer doing that, but let me explain why I did that and why things are changing again. So YouTube, unfortunately, incorrectly gave us a community strike, and so we appealed the decision, and this decision was pulled. It was due to some sort of computer error with YouTube, and so luckily we were able to fix that. They actually marked one of my PDFs that I posted as illegal distribution of resources, but because I mentioned that it's an educational resource, and this is a free educational resource for everyone, they luckily appealed that decision, and we're moving forward. That being said, we are now able to do YouTube Live every Thursday and Sunday at 9 p.m. Eastern Time, which is right now, starting 3 minutes ago. Let's talk about a couple other things. If you're new to this sort of thing, this is how it works. I'm going to be answering some questions, and those questions are actually going to be placed on it's backwards for me. It's going to be the left over here. I'm actually going to show all the math questions over here that you guys post. I know right now it's a little weird because there's some like inception going on with it, but that's because I'm using some sort of software to run this YouTube live session. So there's a lot going on here. That being said, there's more to say. My students are starting school next Wednesday, so I have about 150 to 200 in-person students. So this YouTube live event is going to get huge really fast. Make sure, if you haven't done so already, subscribe to this YouTube channel, like this video, because I want people to know that there is some sort of online resource that people can use to get free help. We will be posting, I know I say this every single tutoring session, but we're actually posting our first math course online. And this math course, let me tell you, it is definitely studio quality. It's gonna be pretty awesome. If you've ever seen something like Vsauce or Veritasium, it's going to be that sort of production quality. And we're going to be addressing first statistics. And then after that, we're going to go into a basic math class, which is like a more remedial introduction to mathematics. So yeah, Jesse, no problem. We love hosting these free courses. I'm a firm believer. Let me just say this right off the bat. As a professor, I'm a firm believer of free education for all. That includes college. So unfortunately, our politicians are not allowing us to give free resources. So we're just going to do it anyways. And we're pushing a little bit of extra effort here. But you got to do what you got to do to get free education to people. And so this is free math tutoring. This is for all ages. Doesn't matter where you are. If you want to know a little bit about what infinity is, if you want to know why 2 + 2 = 4, if you want to know the fundamental theorem of arithmetic and you want to go through the proof of that, if you want to know Russell's paradox, which is a pretty cool request to go off of, you can ask all of those questions on here. So feel free to just in the live chat. I think it's this direction. I hope it's this direction. Post your questions or in the comments section below. Either way, I'll address all of those. by the end of this video. This is going to end around 6:30, 7 o'clock. So if you have dinner, you need to go to the restroom, feel free to do that and come back and just ask whatever math questions you have. So we're going to get rolling right along. We have 6 people here right now, which is not that big, but for a tutoring session, it's actually pretty good. It's not bad. I've never tutored more than 2 people at a time. So let me tell you a little bit about myself, and then we'll get into the questions. I'm a university math professor. I'm here in Arizona, and I teach mathematics ranging from lower division to upper division. I don't teach graduate level courses, but online I do teach Udemy courses. I have right now about 16,000 students, so almost every single graduate student, well, I think there are more students in my classes than graduate students in mathematics, which is actually really cool to see. But if you are in some sort of undergrad math major or graduate math degree, pretty much everyone's on there, which that's been going on for years now. And so this is just a way of making all that stuff free, but also taking really crappy video into production quality. So I have tons of students. We have 8 viewers now, which is really cool. So hopefully you guys can share this link, talk to your friends, talk to your school buddies, go to college, post some, on forums or whatever. If you have some groups, some Facebook groups or whatever, just let them know, hey guys, every Thursday and Sunday we have free math tutoring at this one link. So just go to our YouTube channel and you can subscribe to make sure that you get reminders for these things. Those are pretty helpful. That's actually why we got a big giant group of people that just came in, because most of them just got a little reminder on the YouTube notifications thing up there, and it says, hey, there's a free YouTube thing. So make sure you subscribe so you can get those and you can ask your math questions freely on Thursdays and Sundays. If you have any suggestions for this, feel free to also post that on here. Like maybe you want more days, maybe you want less days, maybe it's too much, maybe it's too little, maybe you want me to go to a different platform. Totally appreciate all those questions. So, all right, let's get started with these math questions. I actually first want to address the math notations question. So there was, I believe this was submitted by Peter, and Peter asked me a really good question. Can we go through some notation stuff? So I'd actually like to go through a lot of notation and then give you guys some resources on how to look through that notation. I think this is Peter. I apologize if this wasn't your stuff right here, but let's take a look here. So let's talk. Well, let me quickly grab a writing utensil here. I have a little writing pad, and I'll be able to make notes on this. So let's see here. And by the way, if you guys have pictures, like something like this, or you have some homework and you want me to go through it, I'll literally go through it with you guys, which is pretty cool. All right, screen sketch. Great. So now I can like draw on this, which is pretty cool, but let me change my color here. So I'm going to dissect what all of these things mean. Let's start with this first one right here. So this symbol right here, this backwards E, means there exists. So actually, this is going to be hard to write down. I will try to not be absolutely terrible with my handwriting. Let's try this. There exists. So that's what this backwards E stands for right here. And why is that the case? What's the history behind that? I have no idea. But people say this phrase so often that they actually just get lazy in math and they write a backwards E. But I have no idea why it's a backwards E. So it says there exists, and then we have this these 2 letters, I and J, and it says does not equal. So this is actually, whenever we talk about the phrase there exists, that means we're making a claim about the existence of something. And so in this case, you'll see 2 variables over here, I and J. I and J are both objects that we're claiming to exist. But we're also making a claim about those two objects. In particular, they're different things. So all this says is that there exists two things, I and j, that are not equal to each other. Now, I and j, whenever we use like letters like x and y, and I don't know if you can see it over here. Let me see here if I can get this. We have this y, this x over here. Whenever we're using symbols like I, j, x, and y, st, typical variable notation, those things are not actually like letters. They're representations of objects. So in algebra, you learn that like x is a constant. Variable is a different thing, but x is a constant means that x is some number, maybe it's 5, maybe it's 10, and it doesn't change. We don't know what that number is. X represents like this curtain. So a lot of ways when I teach my class about constants, this is how I teach it. I'm going to block the camera real quick and explain. Let's say we're talking about a variable here. This variable is x, and right now you see a black screen. The idea is when I lift this curtain, this x is like this black screen. You can't see what's behind the x, but maybe every once in a while you take a peek. And if you notice, what's behind the x is this guy right here. So Professor Amour. Now the cool thing about constant is if I use x again, which is what you're looking at again, it's like this curtain, and I reveal what's behind the curtain again, it's Professor Amour again. So the idea is with constants, they're just representations. They're just like curtains, but there's something behind that. Now in more advanced classes, which I assume, Peter, you're in some sort of, maybe you're interested in some more intricate mathematics. Maybe the idea is you might get into not representing numbers, but representing objects. So that's why I said that behind the curtain is Professor Amour. I and j in this instance could literally represent anything. It doesn't have to be numbers. Whereas in algebra, typically you're working with numbers. I could be an elephant and j could be a hippo. So that's what that means. So let's think about it. Let's think about the first one. Is this true? Does there exist an I that does not equal j? Well, can you think of two things that exist that do not equal each other? Well, I just gave one just earlier. An elephant and a hippo. Those two things are like my I and my j, and I'm claiming they exist. You can go to a zoo and verify this. And they're not the same things. So when you go to the zoo, you'll notice that an elephant and a hippo are in fact different things. And I know I'm speaking in a kind of a condescending way, but it's important to understand that that when we do mathematics like this, most people, have to be sort of obvious, and it's important to be obvious because these things are a little bit more complicated than a lot of people assume them to be. Let me double check real quick before I get to the second one, see if anyone has any questions about this so far. I hope this was Peter's question. Maybe not. No, we have none. So let me briefly wrap this question up, and then I'll address the free notations question. So let me pull this up real quick. Here we go. Screen sketch. There we go. All right. Now this next symbol, this upside down A, which by the way, again, I guess they picked a random letter, E for exists and A for all. And then they tried to flip the A, but realized that the A is symmetrical, so they got to flip it upside down. That's the only thinking I can make sense of here. But yeah, this A right here, upside down A, means for all. And then we have these two constants that we are, well, actually, these are variables, but let me explain the difference here. And let me explain why. When we're talking about for all, I'm making a claim about all objects. So now I'm not making a claim about the existence of objects. I'm making a claim about all objects. And so I'm saying for any object you give me, an x and a y, So now these objects can take not only an elephant and a hippo, it can take on anything. But for any two objects that you give me, any two objects, they're different from each other. Now, that's not true. Now, x and y, they look different, but they could be the same. Keep in mind, x and y, those are letters, and they represent curtains. But the idea is you can pull back the curtains and notice, hey, they're the same things. The curtains look different, but what the curtains represent are the same. So x and y could both be 5. I can have a 5 and a 5 with a curtain x and a y in front of it. And when I pull back the curtain, voila, they equal each other. So this is actually a false statement. So this one was true. This one is 100% false, because not every element, not every two things are different from each other, because you can have, two things that look different, x and y, but then when you pull the curtain behind, you'll see that they're in fact the same things. All right, let's talk about this next two. So these next two are very, very different, but again, the notation's a little weird here. Okay, so I'm going to make an assumption about this. I'm assuming you're in Peter, if you're watching, I'm assuming you're in some sort of introduction to proofs, or you're starting a topology class. But this n here is very awkward notation. This is something that mathematicians don't frequently use. But basically, what this is saying is, let's get rid of this n for a second. If you see this, here, let me get a different color here so I can have emphasis on this, not red, because that would be kind of inconvenient. Green, there we go. This right here. All right, so that is all the numbers between 0 and 1, including 0 and 1. So if you draw the number line over here, you have -1, 0, 1, 2. The idea is the bracket 0 to 1 is all these numbers right here. So this is 0 to 1. Now, when we throw the n here, we're actually referring to the nth dimensional version of this, which is kind of a crazy thing to picture. But the idea is in this, I'm making sure, Peter, if those are brackets, then this is the nth dimensional cube. So right now we have a line, and then if I put a 2 here, that would mean I would have a square, and if I put a 3 there, it'd be a cube. If I had a 4, it's where things get a little weird. But I noticed, Peter, I think this is yours. I hope this is yours, Peter. Whoever owns this question, that right there looks to be like possible brackets. Or not brackets, braces. And if those are braces, then this is a very different set. So we're going to have to maybe come back to that one depending on whether or not that's clarified. So let me go on to the last one. And for all of you guys who are math majors or who have taken the proofs class, you can understand why that notation's a little bit important here. This right here literally means subset. So that this A is inside this guy, U. So basically, what this says is I have a set A, here's A, and then I have this other set, U. And so A is inside of U. Now, A and U are sets, which someone asked me earlier, what is a set? I believe that was the same person who put the Russell paradox question, which is, I apologize if I be smart. Oh, and Jesse clarified, these are braces. Good. Or no, it's not Jesse. Peter clarified that these are braces, which makes a huge difference. So I'll come back to that third one in a second here. So this last one here, we'll get to A inside U, but this is basically, these two things are sets, and A is inside of you. Basically meaning that if you take anything from A, that object is also in you. So I'll give you an example of how this can be true. Let me turn on the notation thing real quick so I can make notes. So I'll give you an example. A is prime numbers. And that is not how you spell prime numbers. Yikes. That was embarrassing. Prime numbers. Let's think about what is something that is bigger, that it contains the prime numbers and maybe some other things. Maybe something like the integers. So in this case, A is inside of you. If you are a prime number, you are also an integer. If I pick anything from the set A, say the number 7. 7 is a prime number. 7 is also an integer, though. And so everything that I pick, any object that I pick from A is also in U. So again, a pictorial demonstration of that last one is I have A here, and then I have a bigger version of U. All right, I hope that clarifies this question. Maybe there's follow-up questions on that. Let me go to part 3 again, because I was under the impression that it was all the numbers 0 and 1, but let me talk about this real quick. So this is basically, this n is basically like an exponent, but with sets it's a little bit different. So I have the set 0, 1 here. So this is a set of two objects, the object 0 and the object 1. Now, I am going to exponentiate a set. Basically, I'm going to multiply sets. But multiplication with sets looks a little bit different. It's called the cross product. If you haven't heard of that, let me explain what it is. But exponentiation is just like multiplying over and over again repeatedly. So I'm just multiplying by the set over and over again. And this right here is a total of n sets being cross product produced. That's a weird, I don't know what the term there is. Past tense. So anyways, and passive voice too. So what does this mean? What is the cross product? Well, the cross product, the way I think about it is sometime when you were in high school, and for those of you, by the way, who are in some sort of math program or proofs class, and you're wondering what the cross product is, this is how I like to think about it visually. When you were in high school, you had this number line, and it looked something like this, and it had numbers on it. And then at some point, your teacher threw at you a graph that had two number lines that were like crossing each other. And that vocabulary is not intentional, and this is like the XY axis, but this is a visual representation of what the cross product is. I'm taking the real line and I'm crossing with the real line. Now, if I can do that 3 times to get if you've taken calculus 3 or multivariable calculus or vector calculus, I have R3 now, which is 3 dimensions instead of 2 dimensions. So this is me taking R, crossing with R, or R cubed. So this is a visual representation of the cross product. But in this case, I'm not crossing the real number line. I'm crossing a set with only 2 objects in it. So what does that look like? Well, let's talk about what this thing is. Let me get rid of that. Oops. Let's go back there. Didn't mean to do that. Let's talk about what this is. Come on, computer. Sorry, guys. There we go. All right. Let's talk about what this is in a nutshell. So this is a plane. It's a visual representation of something, though. It's actually a bunch of points. This is a collection of a bunch of positions, many, many positions. And all of those positions, I'll give you an example of a position. 1, 2. That is one position. Another position might be 3, 4, or 5, 7. These are all different positions on this graph. Basically the graph itself is the collection set. That was set talk right there. It's a collection of all of those dots. So I'm taking I can take any point on this line and put it in the first coordinate there. And then in the second coordinate could be any number from this line. So let's talk about what that looks like in terms of 0, 1 crossed with 0, 1. So this is also a bunch of points. In this case, I'm only crossing two things. So this is a two-dimensional plane thing. But the first coordinate can either be a 0 or a 1. So I'll pick 0. The second coordinate can either be a 0 or a 1. Say 1. And so that is a point on this graph. Another point is 0, 0, or 1, 1, or 1, 0. So these are the only 4 positions. So what this XY plane looks like is dot, 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 dot right there. That is your XY plane. And it looks a little bit different now, doesn't it? Because there's only 4 options instead of infinitely many. And so now if we talk about this n here, this just means the nth dimension. So if I add an extra layer here, a third dimension, let me erase this real quick. There we go. If I have this would be, these points would have 3 coordinates. One from here, one from here, and one from here. So the first number could be a 0 or a 1. Let's say it's 0. Second coordinate could be either a 0 or a 1. So we're picking from that one right now. Let's say 1. And then we can pick here either a 0 or 1. Let's pick 0. So this is an example of a point in when n equals 3. So it's a finite set. It's always a finite set for whatever n is. If n is 10, there's only a certain number of combinations of 0s and 1s that for 10 positions. And that would be 2 to the 10th power. So in fact, this is a finite set, and I can actually tell you that the number of elements is 2, let me get this right, to the nth power. So for 3 dimensions, there's 8 options. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. There's 8 possible options, which is, by the way, 2 cubed, third dimension, so that's 3. So that's a brief rundown of this. I hope that helps, Peter. But let me address your philosophical question real quick. You asked me a really good question about where do I find information about math notation? Is there like a math dictionary? And the answer is, I just got a question about Mobius transformations. Oh boy. Here we go. We'll get there. The answer is yes. So actually, Peter, I grabbed a bunch of books here. These are my favorite books. They're not dictionaries, but they're basically books that you would typically see in an Introduction to Proofs course. So we got the most famous Introduction to Proofs book, which is How to Solve It by Polya. If you guys haven't read this book, this is historically one of the first math books regarding how to prove things. So how to solve it, I said how to prove it. This is how to solve it. And then it has the corresponding how to prove it, which is the newer version. This was made in, I want to say, the last 20 years. Looks like 1994. So when I was born. Yeah, I'm sorry, guys. I'm a little young. But yeah, this book, it's got some rough rough edges, and it's got a lot of dirt on it because I definitely used this book when I was in an Introduction to Proofs course. But this is also a really good like introduction to math notation. I'll tell you where to find it. There's this book, Discrete Mathematics, which for those of you who are interested in learning mathematics and you're kind of new to this whole thing, this is Discrete Mathematics by Susan Epp. This is a great educational resource. And then there's this one's a little weird. This is a different. I had a professor. I graded for a professor with this book. This is called Chapter 0, which I guess is like the beginning of mathematics. But that doesn't really answer your question, Peter. The question was, where's this math dictionary? The answer is actually in the beginning of every single one of these books. So if you take this book and you turn it to the very front cover, I don't know if you can see this. Probably not, because I don't have really good cameras here. I'm not super awesome with webcams, but I do have a 4K camera for my studio quality courses coming up. It's just got a bunch of, I think there's multiple pages. No, there's only 2 pages of just what everything means. Now, this is a really rough like definition. So it says, for example, let me see if I can find that notation we were talking about earlier. The backwards E. Yeah, the backwards E is in here. It says there exists. But like, what does that mean? That's not really a dictionary, because a dictionary gives like examples. It describes thoroughly what it means. This doesn't really do much of justice. And the same thing with all of these books. If you turn to the front cover, you'll see some version of a, you should. Actually, this one I don't think you do. I think it might be in the back of this one. Wow, you know what? This one doesn't even have it. This is another good one. This one does have it. Elementary Number Theory and Its Application by Kenneth Rosen. This one has notation regarding number theory stuff, but it's once again, it has only a brief thing. So, Peter, my answer to you is that there are dictionaries in the beginning of books, sometimes math books, and unfortunately, there's not a lot of clarification. So, if you need any clarification, every Thursday and Sunday at 9 p.m. you can come here, and I'll address all of that. All right. Let's see. I'm not quite sure where to go from here. I'm going to shoot for Be Smart's question on sets. So, because that kind of follows through with that. This one, though, is going to be philosophical, so I don't think I'm going to need any sort of whiteboard or anything like that. So let's talk about what a set is. A set, so I'm going to give there's a lot of definitions for sets, and this is kind of the problem with mathematics is, what is a set? I'm going to give you the naive definition of a set, okay? Naive definition of a set is a collection of objects. Now, that's actually not a really good definition, because you run into Russell's paradox, which I'll talk about that in a second. But the thing is, I'm actually okay with having some paradoxes. If anyone knows what the plural version of paradox is, please post it on the live chat for me. I'm like desperate for that right now. But I'm okay with the paradox happening. There are, if you have ever heard of Gödel, Gödel was a philosopher / mathematician who proved that any set of axioms is going to have some things that are impossible to prove. So here's the idea of what naive set theory is and what rigorous set theory is. The idea is you have to create these axioms. Like these are some rules about the sets. And these are some rules about how math works. And the thing about those axioms is that it helps from paradoxes occurring. But Gödel in the 1950s, I want to say, proved that you actually can't have a system that doesn't have things that you cannot prove, that you can Let me start over. Let me try this. Gödel showed that even if you create a really, really awesome axiom system, a system of rules about math, there's always going to be a few things that are impossible to prove. And that is sort of, in a sense, it leaves you kind of feeling uneasy, because no matter how you create mathematics, there are going to be things that you cannot prove. And there's different systems of mathematics too. So like you said, there's a rigorous set theory, which is the Zfc Axioms, which I'll go through in a second. But let's talk about why this definition I gave of sets is not really good. So my definition of sets, again, was just a collection of objects. It's just, imagine a collection of things. But I'm going to real quickly go to Wikipedia here, and I'll show you guys. You can go with me here. Hold on. Post it up. There we go. Wikipedia, Russell's paradox. So I haven't really engaged too much with Russell's paradox, unfortunately, and that's largely due to the fact that Russell's paradox has to do with like axiomatic set theory, and I am not too concerned with axiomatic set theory. I'm okay having a few flaws in my math. But let's talk about what Russell's paradox is. So this is a paradox that you get when you define a set to be any collection of objects. But the idea is, let's say you have a set, and it is the set of all sets, right? Because if a set is a collection of objects, then you can create any set. Let's create a set that is the set of all sets. Well, let's talk about a subset of that, something inside of that. Let's let R, and this is where it is. I'm going to highlight it on the. I better not have just clicked that. Very good. Let R be the set of all sets that are not members of themselves. So R is going to be a set of every set that is not a member of itself. So if a set is a collection of objects, you can define a set to be inside itself. So let R be the set of all sets that are not members of themselves. If R is not a member of itself, then its definition dictates that it must contain itself. And if it contains itself, then it contradicts its own definition. So let me explain what this means. R is all of the sets that are not in themselves. Which is kind of weird. But the thing is, if R is not a member of itself, if this set of all sets is not inside this set of all sets, then the definition actually contradicts itself, because R is the set of all. And this is where things get really, really weird. People start like, whoa, I'm getting super, super lost. But the idea is it contradicts itself. When you start talking about the set of all sets, things get really fuzzy. And unfortunately, I don't have a way of like visualizing this. I have no real good conception of the set of all sets and what that would be. But the idea is basically, once you talk about the set of all things, does that include itself? If it does, let's talk about all the ones that do not include itself. And let's realize that R should be inside itself, but it's not. Most people are just like, whoa, what the heck? What's happening there? It's a rigorous proof. It's kind of like Gödel's proof, who made a very complex thing. But I would highly recommend that you check out, be smart. You should check out Numberphile on the Russell's paradox. They should have something like that. But definitely check out their video on Gödel. Numberphile has a really, really good video on Gödel's proof regarding axiom theory. Now, that being said, I do want to mention rigorous set theory. What is rigorous set theory? Rigorous set theory is this right here, which is, let's not use that definition a set is a collection of objects. That's kind of weird. Let's make these rules and let's add to these rules. And people are constantly adding to these rules every like few decades. But this is the Zfc Axioms. I believe it's a list of 12 axioms. I think they're up to 12, maybe not. No, they're up to 9, supposedly. I believe you can go further than that. But I want to go through these real quick. Here are some rules about sets. So it's a collection of objects, but here's a couple things. Two sets are equal if they have the same elements. So that's basically saying that you can't have two sets that have the same objects but that are different in identity. So just because two things have different names doesn't necessarily mean that they're actually different from each other. So names are not, identity is not, does not make something separate from other things. The same idea, by the way, applies with names of people. My name's Cody, but there are a lot of other people that are named Cody, but I'm one specific Cody, and the only way someone else can be the same Cody as I am is if they are also me, which is not possible. Axiom of Regularity, which says that every non-empty set X contains a member Y such that X and Y are disjoint sets. So basically, if you have a set, you can find something in there, and then you can find something else where those two things are not the same things. That seems kind of obvious. Like, let's talk about, like, for example, the prime numbers and the integers. You can find a prime number, but can you find something that is not a prime number that is not in the set? 4 is a composite number, or pi. You know, these are things that are not in the sets. And so that's true for every set. You can find something in that set where you can find something outside of that set. Let me see here. The axiom. So after this things get kind of weird. But if you're interested, I wouldn't go any further than that. Axiom of Infinity is pretty cool. I believe this is the one where it says that there are two infinities, but there's no middle guy there. Someone fact check me on that one. And the last one is the most important one. Everyone, if you're paying attention, the well-ordering axiom is like the most fundamental theorem in axiom theory. The well-ordering, it should be called the well-ordering axiom. It's called a theorem because there are different versions of the well-ordering axiom. Basically, for any set, well, this is a really bad definition. Let me give you the gist of. Let me tell you what the well-ordering axiom is, and this is part where I believe set theory becomes fun. The idea is if you take the natural numbers 0, 1, 2, 3, and actually I'll even write this out. So let me pull up my notepad here so you guys can see. So if you have the natural numbers, which by the way, Peter, there's a name for this. That's the symbol for that, if you ever see that. So this is the natural numbers. I believe that it includes 0, but there is a large debate in mathematics whether or not that thing is really a natural number. Is it natural? I don't know. I think it is. I really do think it is. So that being said, let's talk about the natural numbers, what the well-ordering axiom says. If you pick a subset of this, so pick A, that is a subset of this natural numbers. Now, if you pick any subset of this set, basically A has a smallest number. So let's pick a subset of the natural numbers, the even numbers. What's the smallest even number? 2. Prime numbers, what's the smallest prime number? 2. Odd numbers, what's the smallest odd number? 1. Numbers that are divisible by 17, what's the smallest natural number there? 0. Threw a curveball. Actually, even numbers would be 0 as well. mess that up. But because 0 is technically divisible by 17. But the idea is you give me any set inside n, I can find you the smallest element. It's not going to have two elements that compete for that title. So it's also not going to have a bunch of large elements. There is going to be a smallest element. So that is the well-ordering axiom in a nutshell. All right, so we have a couple different questions here. The Mobius transformations. Unfortunately, we didn't get to that. I'm actually not very good with Mobius transformations, but I will address that in the next live session. Let's see. Peter mentioned he liked my elliptic curve cryptography course. Kevin just finished my Udemy course, Math Proofs. Let's see. You're studying Rudin's book, Principles of Mathematical Analysis. It's a good book, not bad. You have a question. It said, my question is based on irrational numbers, how he shows that there is a set that contains no largest number and a set that contains no smallest number. Yeah, I know what you're talking about. I'm blanking. What question is he talking about? I understand exactly what you're talking about, Kevin. Let me address that real quickly. So this is actually how the irrational numbers are created. So numbers, here's the thing about mathematicians. We just create numbers willy-nilly. And if you haven't done so already, check out Vsauce. And go to his, what is it called? Ordinal numbers. Ordinal infinities, actually. And in this Vsauce, Michael, he talks about the different ordinal infinities. And basically, he just talks about creating new numbers. Just adding infinity to the number line, and then adding infinity plus 1 to the number line. What does that look like? And you can do that. What's 2 times infinity? It's 2 times larger than infinity. Things get really weird, but he talks about just making up numbers. Mathematicians actually did this with irrational numbers, and let me show you how. So you have Q, which is just the fractions. Anything that could be represented with a fraction. Now, unfortunately, there are things that are not in this set. So let me give you an example of a thing that is not in the set. Me. I am actually not in this set, which, Peter, if you're still watching, that symbol right there means is an element of, and then the cross means not. So Cody is not an element of the fractions. I'm not a fraction, truth be told. But there's also something that looks like it should be a number, but it's not in this set. So we look at this and we're like, I got all the numbers. All the numbers are in this set. I found them all. They're here. And then someone's like, not exactly. I can find something that's not in there. That should be a number. Let's look at a subset for this. Let's talk about all the numbers. Now, I'm actually going to put an X here, and I'll explain what that is. But let's take the set of all numbers. I'll put numbers there. Such that, that number right there means, or that line means such that. Ugh. All numbers, and by the way, I'm going to use X. All the numbers X such that X squared is less than 2. So give me a fraction. Looks like this should have a bunch of numbers, but now X squared is less than 2. Let's think of a fraction such that if I square it, it's less than 2. 1. 1 is technically part of the fractions system. 1 over 1 is 1. 2 over 2 is a fraction that is 1. If I square 1, I get 1. So 1 is in this set. 0 is in this set. 1/2 is in the set because 1/2 squared is 1/4, and 1/4 is less than 2. There are a lot of fractions in this set. But the thing is, this set doesn't have a maximum element. Like, the idea is there is no maximum element. And let me explain what I mean by that. If you've taken calculus, you've seen something like this. That is notation for all the numbers between 0 and 1, but not including the number 1. Does this set have a maximum element? And the answer is no, because let's think of a number that might be the maximum element of that set. 0.9, that's really close to 1. Ooh, darn, actually 0.99. No, even closer, 0.999. No, I can find an element closer, 0.999. And the idea is, you can't give me a maximum element, because if you give me any number in that set, I can find a number that's even closer to 1 than that. So in the same way, this does not have a maximum element. You give me a fraction that satisfies this equation right here, then I can find a fraction that is bigger, more maximum, more larger, that also satisfies. But the idea is you can't find the biggest fraction that would satisfy that. And so there's a missing element here. What do we do with these missing maximum numbers? Well, let's talk about that in a second here, but let's go over here. We don't have a maximum element with 0, 1, so let's think what we can do here. Let's add the maximum element. Let's add an element. And that element is going to be called, I'm going to give a funky symbol. There, that's a random funky symbol right there. But this element is the maximum element. I'm adding an element that is the maximum element. Okay, this element, by the way, is 1. 1 is an element. We'll title that as the maximum element in that set. The idea is an element that is the maximum. I'm going to force like this max on this set. And if you've talked about supremums and infimums, this is a supremum. I'm going to add a supremum, and that supremum is going to be called this, square root of 2. And so I'm creating this number, and this number we can actually prove is not a fraction. It is outside of the fractions. So I found this number that is outside of the fractions. Let's add that to my list of numbers. So I'm going to take Q, and I'm going to add the square root of 2 to this list of numbers. Now I have a number system that's even bigger. And I keep adding the numbers, all the different irrational numbers. And then eventually I get, once I add all the irrational numbers, I get R. But then I find another number that I can add that makes things a little weird. This other number is the square root of -1. What do we do with this guy? This guy isn't a real number, and you can prove that. So we add that, and we add all versions of this complex number. And eventually we get, a lot of you guys are anticipating this next part, C. And then we can start even going further, but C is a pretty nice set. Complex analysis is a beautiful thing, but maybe we could save that for another day. But Kevin, I hope that answers your question. What I recommend, Kevin, is check out, I actually don't, real analysis. Just find a real analysis book. And Rudiman, I think, is the author of real analysis that I would recommend. Maybe he has a complex analysis book as well, so take a look at that. All right, we're almost done with these questions, but if you guys have any questions, make sure you post over here. Let me give you guys a quick rundown of what this thing on the bottom of the screen is saying, and then we'll get into, I really want to get into that Hill Cipher question. That Hill Cipher question was beautiful, which was number theory. Okay, Kevin, that helps out. I don't know. The idea is there should be this number that is like the next number to the set that I was talking about, but there isn't. It's not a fraction, and it's weird. And so the idea is you find this thing that's not a fraction, and so you throw it in there. That's a brief rundown review of what I just said. I hope that helps. But that one's one of the most difficult proofs for professors to go through because there's so much involved. And they do it in, I'm guessing, Kevin, your teacher covered that in a matter of like 5 minutes. At least it felt like 5 minutes. It did for me. And then I went home and studied it for probably about 5 hours. And still didn't get it. And got to be in my math proofs course. All right, what else do we have here? I think the Hill Cipher is the last question. James mentioned that he wants me to check out r/math. I posted r/math, and I posted this video, so hopefully people can see that. Oh, Nuno was Nuno. I can't really tell if there's a squiggly because YouTube doesn't allow me to say that, but said that it was paradoxes. That's a weird word, paradoxes, not paradoxes or whatever the plural is. All right, I think we are left with the Hill Cipher question. So let me make sure I've addressed every single thing. I'm going to real quickly pull up on YouTube. If you have not subscribed to this channel, make sure you subscribe on the button below here. That way you get a reminder that we have these free tutoring sessions every 9 p.m. Eastern time. So make sure it's Eastern time on Thursdays and Sundays. So just like today's Thursday. Let me pull up my list of questions that I got from last Sunday. And again, if you guys have any questions, last minute questions, throw them up right now and I will address every single one. But let's see here. Yeah, so this is by Akash. Asked me 8 questions regarding the Hill Cipher. Now, there's a lot. This would be another 3 hours if we did this. So for that reason, unfortunately, I don't think I'm going to be able to address all of these, but let me show you guys some cool math. If you guys are basically reading into math, like you're introducing yourself to more advanced math topics, this will be a cool number system I'm about to show you. So let me pull up my whiteboard, and I'm going to talk about a really cool number system. So we talked about R a little bit. We talked about the irrational numbers, but let's talk about this thing. What is this thing? This is the integers. So these are numbers like 1, 2, 3, 4, also 0. Also the negative integers, -1, -2, -3, -4, -5. And I'm actually going to draw Z using like this weird mapping here. Let me make a better version of that. Here we go. So this is my Z, and this is all the integers in this set. What I'm going to do, and this is a very weird thing, I'm going to separate this into 8 groups. One, two, three, four, five, six, seven, 8. And so the idea is I just took every integer and put them into 8 groups. And these groups are going to have titles. 1, 2, 3, 4, 5, 6, 7, and I'm going to use 0. Now, the idea is I'm redefining all the integers to be one of these objects. 0, 1, 2, 3, 4, 5, 6, 7. So those are the 8 objects that I have. Now, if I give you an integer, how can you tell me which group this is in? Which group is it in? The way you do it is you take your number, you divide it by 8, give me the remainder, and that is your group. So take, for example, 10. What is 10 divided by 8? Well, use the division algorithm. I'm going to do the division algorithm over here. So 8 into 10. It goes in once. And I'm left with the remainder of 2. So I take that remainder, and that is my group. So we took the number 8. We took the number 10. That was the number that we used. And we stuck it in this group. 10, the integer 10 is now 2. Let's take another integer. Let's do, let me think of a number here. 18. How many times does 8 go into 18? It goes in twice. So we minus 16, and we're left with a remainder of 2 again. Hey, okay, that's interesting. The number 18 is also in this group. Let's think about this group. What gives me a remainder of 0? Pretty much everything divisible by 8. So 8 is in that group. 16, 88 is in that group. What about 5? What's in this group? 13 is in that group, because 13 divided by 8 gives you a remainder of 5. What else is in this group? 21, 29. All right, so you could see how I took the integers and I separated it into 8 objects. And these objects we can do math with. And this is where things get really bizarre. So I have the objects 0, 1, 2, 3, 4, 5, 6, and 7. This right here, I'm going to call the integers, but I'm going to give a little something right here called 8. Now, this is pretty interesting stuff, but the idea is if I can do math with these things. I'm going to take, remember, I'm going to go back to Z real quick here, my integers. Give me 2 integers, like 5 and 10. Let's do 5 and 19. Okay, 5 and 19. I can add those 2 numbers, and that is 5 plus 19 is 24. But what number is this in Z8? Well, it happens to be 24 divided by 8 is 3 with a remainder of 0. So the remainder was 0. So this 0 is actually 5 plus 19. And a lot of people are going, what the heck is going on here? But let's do this math problem in this universe, Z8. So 5 is in group of 5. 19 is divided by 8 is 2 with a remainder of 3. What's 5 plus 3 is 8, but 8 gives me a remainder of 0. So it's weird, but you can do some funky things with this number system. You can add numbers, subtract numbers, multiply numbers. It turns out like if you take, this is going to be pretty bizarre to some people, but if you take any object from group, and I'm going to be working in this number system now that you're looking here. If I take any number from the group 2 and I multiply it by any number in the group 4, I end up getting 0. Let me show you. Think of a number that gets a remainder of 2. when you divide by 8? 18. Remember 18 was in that group? So 18 is the integer. By the way, now we're in Z, the integers. 18 gets a remainder of 2. Give me something with a remainder of 4. Let's do 12. What's 18 times 12? Let's put a 6 there. 2, carry the 1, 3, 0, 8, 1. This comes out to be 6, 1, 216. But if you divide by 8, that gives you a remainder of 0. So 2 times 4 equals 0 in this universe. That's really bizarre. That's really, really bizarre. I'll give you another one that's kind of weird. 3 times 3 equals 9, which is 1. So 3 times 3 is 1. That's pretty strange. So you could test this stuff. If you're interested in this weird math and getting a really good understanding, I recommend Elementary Number Theory. This is Kenneth Rosen. Kenneth Rosen's really good. Now, to the last guy who wanted me to go through the Hill Cipher. If you're interested in a Hill Cipher textbook, Introduction to Cryptography with Coding Theory is a great resource for that. You can check that out, and if you get that resource, Washington, Lawrence Washington, and I've met Professor Dr. Washington. He's a great guy, but his book is really, really good and insightful about the Hill Cipher. I recommend checking that out. Also, take a look at my number theory course and my cryptography course. If any of you guys are interested in my Udemy courses, they're all 100% free. I will give you guys every resource, by the way, that I'm giving you, you can get at your local library, or you can get it at your you can get the resource at a local library or at your university library. But let me give you guys a coupon code here. It is Amour Learning, all caps. If you go to any of my Udemy courses, you'll get it for free. So these are all free resources. Highly recommend them. If you're interested in purchasing them, they're really good education resources. So take a look at them. Anyways, that is my Thursday math tutoring session. You guys could please share this with your friends. That'd be awesome. That way we can spread the word. You guys can ask all your math questions. I do address them all. Also, make sure you subscribe. Hit that button down there. Subscribe to our YouTube channel. That way you can get reminders of these free math tutoring sessions every Thursday and Sunday at 9 p.m. Eastern Time. Remember, we do YouTube Live, so if you're on Facebook and you're trying to find this, then you're going to have some difficulties. So just keep that in mind. Anyways, I'm going to give you guys about 3 minutes. We're going to do a quick break. If you guys have any math questions, feel free to post them on the live chat over here. I'm going to real quickly put on some music and a BRB thing. And if we have more time, then we will address more questions. So again, put your questions in the live chat over here or in the comment section, and I will address them shortly if we have more. So no problem, Peter. You're welcome. I'm going to put this back up, and then I'll come back if we have more time. Thanks, everybody. Again, one more thing. Liberal arts math is going to be posted in 1 week. 120 lectures, studio quality. That will definitely get this YouTube channel up to, I'm hoping, Veritasium level, which would be really, really great. So, and then eventually we'll be able to get professional lighting in our free tutoring session, because it's a little dark right now. I don't know if you guys can tell. And I actually have some lights that are turned off, which is kind of stupid. So thank you guys so much. And post your math questions on the live chat. And if I have any more, I'll get to some. So have a good week, everyone. And we'll be back on Sunday, 9 p.m. Eastern Time. See you then.